So welcome everyone to the second part of Zhou's lecture. So over to you, Ting.
Okay, thank you, Venki. Thank you for coming back. Just to quickly recall that we are at the second part of my talk, essentially looking at inverse boundary value problem for nonlinear Maxwell's equations. So as I have introduced a little bit and shown you the linearization approach, like first order linearization approach in solving some inverse problem for nonlinear conductivity equations. So for Calderon problem, and the same idea can be applied to inverse problem for Maxwell's equations with nonlinearity. But let me start this part by showing you what kind of applications, potential applications of this theory by considering utility of nonlinear optics in imaging, for example. So this is a slide to motivate the whole problem. Is that why you want to sometimes recover the nonlinear property or electromagnetic property or optical property of the medium. So this kind of imaging process could and was explored, and there were several technologies using nonlinear optics, say two-photon excited fluorescence, and using second harmonic generation in the microscopy. And there are some theoretical and developing image modalities called coherent interferometric imaging, using also second harmonic generation scatterers. So these are all focusing on recover the nonlinear property or nonlinear electromagnetic property of the material. And the advantage of that, in principle, is that it has better depth penetration, so you can look deeper, and also stain-free molecule contrast that allows you to use less contrast fluorescence, for example. Okay, so I hope this convinces you that sometimes using the nonlinear property of the object as an imaging method could give you different information about this material. And then to model the nonlinear optics using Maxwell's equations, we go back again to the original time-dependent Maxwell's equation. In this case, no charge and current density for simplicity. So I used a different notation here. I apologize for that. This is coming from the old slide. Sorry. So, however, it's the same story, except that instead of assuming linear constitutive relation, we assume nonlinear relation, of course, with the linear part. Still, you have epsilon E and the mu H. And you have nonlinear, this is called the electric polarization, and M here represent the nonlinear magnetization. Okay, so I dropped the conductivity parameter in here, but you can easily add that to epsilon, allowing epsilon being complex. So just for, in the general case, we just allow epsilon and mu both together to be complex valued functions. Okay. So you can think of imaginary part of epsilon being the conductivity in the Maxwell's equations. Okay. So PNL and MNL here carries the nonlinearity in the equation. Let me briefly talk about the nonlinearity mechanism here. So in nonlinear optics, the polarization in general consists of the linear part and nonlinear part. So we put the linear part just directly together with the linear constitutive relation part. So we just forget about this thing here and focus on the PNL. So this is a kind of a formal expansion. This is writing in terms of the powers of electric field, rigorously, you should think of the chi2, chi3. These are J+1 tensors. Okay, they acting on the one forms E, and for M and L will be on H. Okay, but you do have something like this kind of nonlinear Taylor expansion you can think of for the polarization. Okay, so second order polarization usually happen in non-central symmetric media, such as the collagen fibers we've seen earlier in the rat tail tendon, for example. So you have this muscle thing with the second harmonic generation. This is considered second order polarization. So you are looking at this second order term here. And to eventually get the time harmonic version of the equation, so you consider again time harmonic instant waves. Okay, and we are particularly focusing on the second harmonic generation. That is when you have a doubling frequency situation, like two photons of the same frequency omega and merge together to get one photon of double frequency 2 omega. So that's a typical nonlinear optic behavior for the material. And the same thing, you can do the third order polarization. So you have, if you have in general case, incident wave of 3 frequencies, you could possibly get new waves with frequencies of any kind of combinations of these 3 frequencies. So this is basically in general called sum and difference frequency generation. So these are all nonlinear effects in terms of the frequency. And what we are focusing on here, one nonlinearity is called the Kerr type, the other is called the second harmonic generation. Okay. So for the Kerr type, okay, so we assume our electromagnetic fields time-dependent solutions for the time-dependent Maxwell's equations of this kind of format. Okay, for the Kerr type, you can think of it as in 2 ways. First is to not think of the polarization as a nonlinear powers, but think of as sort of this so-called susceptibility. Okay, this chi parameter, electric susceptibility, multiplying your electric field. But this susceptibility is not only depending on the X variable, but also depending on accumulation of electric intensity. Okay, so this is a so-called kind of memory term of the past intensity. So when you have this kind of assumption, then you will have a third order kind of dependence on the electric field for this kind of time harmonic electric fields. Okay, same thing with magnetization. You can do the same thing, assuming that chi m depending on the memory term of the magnetic intensity, and you have this sort of third order nonlinear term for the magnetic field. Okay, the other way to think of a Kerr type nonlinearity is to use what we consider the power expansions of magnetization, the polarization and magnetization. So think of, you have an instant wave of a single frequency, and you could have omega plus omega minus omega. So really you have some nonlinear polarization there happening, but as a result, you still get the field of only frequency omega. So that's the case and kind of nonlinearity we're focusing in Kerr type. As a result, no matter which way you are taking to understand this whole nonlinear Kerr type nonlinearity, the result is that this will be the simplest nonlinearity you can define, meaning that you don't have new frequency waves generated. You only have omega frequency time harmonic waves. So as a result, we only need to consider one set of Maxwell's equations only for frequency omega. Okay, so this is a Kerr type. As a result, you have, as I mentioned, nonlinear time harmonic Maxwell's equations. You still have the linear part, but also you have nonlinear third order terms. This A, B will be the previous third order susceptibility, but here we just assume the very isotropic case that they are being scalar functions. Okay, So for this simple nonlinear equation, looking at the time harmonic equations, they are just simple. We just introduce the third order nonlinearity into this Maxwell's equations. But before I was just establishing that indeed in reality, you do have this kind of nonlinearity observed in experiments. Okay, so the inverse problem is to determine not only the linear property mu epsilon, but also the nonlinear susceptibility coefficient A and B from the boundary admittance map as before, the tangential electric field to tangential magnetic field. Okay. Before I talk about the proof of showing the uniqueness, let me also mention for what happens for the second harmonic generation. It's a slightly more complicated than the Kerr type, meaning that you do have double frequency waves generated because of this doubling, second harmonic generation, like two photons of same frequency omega generating a photon with 2 omega frequency. So you should look at the solution with two terms, one involving time harmonic waves for frequency omega, the other with 2 omega, which means if you plug in this into the Maxwell's equation, you will have a system of essentially two sets of Maxwell's equations, one for E omega H omega for the omega waves, and the other set for 2 omega waves. But these are coupled together by the second order nonlinearity, these two terms. So chi2 here will be called the second order susceptibility coefficient. Okay. So from here, you can think about generalize this a little bit more, meaning that I can assume for mu and epsilon, this linear property is also depending on frequency. Later we'll see, actually, if we do assume this, we can still recover the mu epsilon, assuming them depending on frequency.
So Ting, I have a question.
Sure.
So is there any particular reason why the product with E2 omega that is missing?
Say that again, E to the omega.
No, so the quadratic or the product nonlinearity with the E2 omega corresponding to 2 omega, the frequency 2 omega, with the same right. 2 omega. Is there any particular reason why we are not seeing that term?
Sorry, you mean they are not down in the...
I see E omega and E2 omega, and then I also see in the fourth equation E omega.
Right.
But I'm just curious as to, is there any particular reason why we are not seeing the product with E2 omega?
Oh, I see. Yeah, so that's E2 omega and E2 omega will give you the E4 omega essentially. So the question really is that I guess it's also not so rigorous in the modeling. It's only you can think of this. We only assume that the resulting electromagnetic fields can be only of omega and 2 omega, or in other words, physically, you only see the doubling effect of two photons of frequency omega merged together to 2 omega. But the same effect not necessarily happening, or same intensity not necessarily happening to 2 omega merged with 2 omega together as 4 omega. So they are not really comparable. I think the second harmonic generation is more common than any. But I think that's a reasonable question.
Okay.
I don't know,
right.
actually. I shouldn't say that I know the answer, but I can only say that indeed for this system, for this modeling, we only focus on omega generating 2 omega, I guess. Yeah, there's some kind of restriction of this modeling.
Yeah, thanks.
But yeah, here it will be corresponding E omega generating 2 omega, and this will be feeding back E2 omega with E omega conjugate to give you back again omega. So this modeling assuming these two effects being the strongest, I guess, and the only effect in this whole model. Okay. So yeah, for Chi2, if you recall, it should be a 3 tensor. And for simplicity, or we here assume they are being isotropic, that means we should assume them being vector valued. For simplicity, I didn't show the magnetic side of the nonlinearity. So only introduce, you can introduce a similar nonlinear magnetization to this system as well. But also that was not really observed too much, actually, any nonlinearity in terms of magnetic field. I think the only physical observation of that happens kind of macroscopically in metamaterials. So these artificial materials used in this transformation optics ideas. Okay. All right, back to the second harmonic generation. When we have this system as our model, we have two types of fields. Then our admittance map also involves more information for both frequencies. You have a tangential electric field and tangential magnetic field. So inverse probably to determine epsilon mu and Chi2 from this. And keep in mind, Chi2 is a vector valued function. Okay. Yeah, the next two slides are a little bit dense, but what I'm trying to show here is that they are well-posed boundary value problems. So the PDE boundary value problems are well-posed. Hence, you have well-defined admittance maps. Okay. Here it just looks complicated, but these are adapted Sobolev spaces for corresponding systems. And they are LP space. So essentially, this is saying when your boundary tangential boundary condition being small enough in this space, then you are able to show that solution exists and uniquely and has the uniqueness. Okay. And this one is for the well-posted for the second harmonic generation. Okay, the next two slides will be just stating our result. This is a work with Yarnet and Silbekov. So this is for Kerr type, and this is for the second harmonic generation. Essentially saying that we have identical boundary admittance maps for both cases. Then we have unique determination of the corresponding linear parameters and the nonlinear parameters.
Hello, Zhou, can I ask a question?
Yes.
This is Rohit. So this condition on P comes primarily because of the nonlinearity, the order of the nonlinearity, or is there any other reason?
Say that again. Sorry, I didn't.
So the condition on this P, that P is bigger than equal to P is strictly bigger than 3. This is due to the kind of nonlinearity you are taking, or is there?
Yes. Essentially, what we are doing here is using a contraction mapping argument, where essentially you need to establish a contraction map where you use the Sobolev embedding.
Yeah, basically you want somehow this S to be in some LP space, and that is how this restriction comes, I guess, right?
Right, exactly.
I see. And one more question. So why can we add nonlinearity with respect to E in the first equation itself? Like, so in the first equation, this del cross E, you have the nonlinearity term corresponding to H only magnetic field, right? So can we have nonlinearity with E also here, with electric field, or?
Oh, you mean adding to this equation here?
In the first equation.
I mean,
since we are taking the derivative, I don't know. I mean, if that makes physically sense or not. But the thing is, the equation is in E, so I'm just asking that if we can put some non-linearity with respect to E here also in the first equation.
Yeah. you're right. Maybe, yeah, only from PDE point of view, if you look at the system as it is, maybe you want to add that. But if you want to derive the same thing from the original Maxwell's equation, time-dependent Maxwell's equation, it's probably not physical.
Not there. I see.
Yeah, that's just, yeah, my guess.
I mean, so one reason why I'm asking this, like sometimes what you can do, you can just try to combine these two equations to get a single equation either for E or for H, right? And then basically if you add just one non-linearity with respect to one of them, then so I don't know whether that will help or not. I just wanted to ask that if we can, if you can add some non-linearity here with E, and then I don't know.
Right, I'm not sure. Yeah, I've never thought about like adding some term to the first equation. Yeah, maybe it could.
Yeah, I mean, I don't know if that physically makes sense or not. I'm just,
Right. Well, yeah, it's good to try though.
Yeah.
Thank you. Right. So here are the inverse problem uniqueness. Right. So this is the brief idea of the proof. We'll take the Kerr type, for example. As I mentioned before, you can do the first order linearization as what we did for the nonlinear conductive equation for the Calderon problem before for the special case. But here you can also look at the other terms in the expansion. So all the equations, of course, here they have the 0, 0 as the solution for the original equation for the second harmonic generation or the Kerr type. Okay. Then you just look at the perturbation from 0 solution by SF, and this also is consistent with the well-postness result. So you don't take S to be very large. Eventually, you have to have this expansion for S being small. Okay. But what you get is from the first term in the expansion, what you get is the admittance map associated to the linear Maxwell's equation, epsilon mu. So this you can immediately use to recover epsilon mu. Okay. And to recover A and B, then you need to use the next term in the expansion. Notice that there's no second order term because your nonlinearity is third order term to start with. So you only have the third term in the expansion. But you have this tangential of H3. Essentially, these are the fields generated by the linear fields, the nonlinear interaction of linear fields. So E1, H1 here being a linear solution for the linear part of the equations. And then you have them interact together as a new source to give you E3 and H3, the new fields, to account for this third order term. Okay. So this is basically what you think of. F generate linear fields E1, H1, and they interact nonlinearly and becomes the new source for E3 and H3 without any boundary source. So that gives you mu cross H3, the tangential of H3. So as I mentioned, the first order term can help you to determine epsilon mu uniquely. And the next term, third order term, gives you this map. And from this information, you can derive a different integral identity from the linear problem. The linear equation problem is that you will get here the difference of the two sets of nonlinear coefficients, A1 minus A2 and B1 minus B2, and integral against the product of essentially 4 solutions. Okay, and keep in mind E1 and H1, these are solutions for linear equations, and the E tilde and H tilde here are also solutions for linear equations. Okay, so you can see here it's very similar to the inverse problem for linear equations, at least for the Calderon problem. All right, bear with me. Going back to the proof for the Calderon problem here, you have a difference of the potentials multiplying the product of the two solutions, U1, U2. But here, these are the solutions to the Schrodinger equation. For us, here would be the solution to the linear part of the nonlinear equation. Okay, so this is a Kerr type. This is what you get. You have a product of 4 solutions because the nonlinearity is third order. So you have one more. For the second harmonic generation, again, you have the first order term in the expansion, which helps you to determine epsilon mu. But here, as I mentioned, since your first order admittance map has the 2 parts, essentially have the 2 admittance map for omega frequency and 2 omega frequency. So you can really allow your epsilon mu also depending on frequency. You can still recover information just because you have more measurements here. Okay, but we focus on recovering chi2, the second order susceptibility, by looking at the second term. And the same thing, you have the E1, H1 being the linear solutions, and they interact nonlinearly and becomes the source for the E2 and H2 to generate new waves, new fields. And using the second term, you can derive this integral identity. And here would be the difference of chi1 and chi2 multiplying the product of 3 solutions. A slightly different thing, but because of you have 2 nonlinear terms there. So, and the question now becomes again, can we plug in proper solutions? Keep in mind, these are all solutions for linear equations. Okay, so proper linear solutions so that we can recover chi1 minus chi2. Here is just repeating the previous slide where we construct CGO solutions. So spoiler alert here is that the solutions we're going to use are CGO solutions. The differences here is that just for completeness, I put this slide here just to help you to review the previous technique, reducing the Maxwell's into this first order elliptic system. And then you essentially reduce it to the Schrodinger equation to construct CGO solution there. As I mentioned here, yeah, actually here would be a discussion of using the CGO solution with different exponential phases. So before we have x dot zeta here in the CGO solution for the Schrodinger equation. That's what we call the linear phase. Okay, you have the amplitude, you have the remainder. The remainder is supposed to be small with respect to a large parameter tau here. Okay. So for the Schrodinger equation, yeah, this is what I answered Venki's question earlier in the first hour about the sort of partial data results, where you actually can construct the CGO solution for the Schrodinger equation using the Kalman estimate. Okay. And the first one is the original paper by Sylvester and Woman in 1987, where you use the linear phase, and you can construct the CGO solution. And I guess in the next 2 papers, they use the nonlinear limiting column weight to derive column estimate with a nonlinear phase here. So one is using phi x being minus natural log of x, and the other is in terms of the cylindrical coordinates of the space and constructing this phase for the exponential, where r here is the polar direction, polar variable. Okay, so this last 2 will be all for nonlinear limiting column weight, which you can derive the column estimate and prove that you can construct the CGO solution for the Schrodinger equation. Okay. I guess for Maxwell's equation, as I mentioned, the difficulty always is how to get back to the Maxwell from the Dirac system, the first order elliptic Dirac system. This is again just repeating the analysis for that part. Essentially, you want the two scalar potentials being 0. And I did mention that it's not coming freely. You have to choose the amplitude. Keep in mind, this is the CGO for the Y, for the Schrodinger equation, and A is the amplitude there. And you have to choose, you do have the freedom to choose this A with less restriction, I guess. And then you have to choose that carefully so that you have a new amplitude for your X. X is the solution for the first order elliptic system. And in order to get the X1 and 2 scalar to be 0, you need to make sure that this amplitude for the 2 scalar potential to be 0. And the remainder thing in the first and third component, the scalar potentials will be 0 by showing a uniqueness improving kind of the conjugate equation what we can show in construction of the Schrodinger equations. So that uniqueness is not always true when you use the you're using column estimate approach. Okay, so suppose that we are able to do all these steps and have the CGO solutions, and we want to plug in them into the integral identity we obtained for Kerr type, where we have a product of 4 solutions. Okay, and we first try the linear case when you have a linear phase for the CGO solution. This will be the corresponding amplitude if you use the Euler-Sommerseller reduction. Okay, this is a little bit technical, but this would be the complex variable or weight you choose for your exponential, and the dot product of them being the waves number square, and then magnitude going to be large. Then you get a smallness of the remainder terms. Okay, I put S0, T0 here. Also, kind of you have the freedom to choose them to promote electric field or the magnetic field by choosing S0 being 1, T0 being 0. So you can do that in order to get rid of the one term in order to recover A1 minus A2, or get rid of the first term to recover B1 minus B2. Okay, so that's the general idea. However, when we are trying to plug in these linear phase solutions into this identity, and we realize we cannot find zeta 1, zeta tilde, so zeta 1 corresponding to E1, zeta tilde corresponding to E tilde, such that we do have the Fourier say e to the I could c exponent, so that we get A1 minus A2 Fourier transform. We cannot do that, no matter how you choose this zeta. Okay, so it turns out that what we, or at least one thing we can do to improve this is to do polarization. And it's different polarization, meaning that you can take a linear solution being a superposition of 3 solutions, and then you can have more complicated terms. But what you're really doing here is that instead of just in the expansion here, instead of taking only SF omega, you can take 3 sources, F1, F2, and F3, and to have different directions of perturbation, so you can get same kind of integral identity as here. Okay, it looks longer, but what the improvement is that you do have a product of 4 different solutions instead of 3 same solutions with the second one. So that's slight improvement. Okay. However, we still have issues using these kind of CGO solutions for the Kerr type. Let me come back to this problem, but before doing that, I wanted to explain a little bit why that could fail when you're trying to plug in the linear phase case. But what we did here, actually, we used the CGO solutions with cylindrical faces. And this is the only case that you were able to use the Kalman estimate, or actually, yes, Kalman estimate to prove the uniqueness and to show that you can construct the CGO solutions for Maxwell's equations. And these are the CGO solutions we chose to plug in this integral identity here. And eventually we are able to recover A1 minus A2 by, it's a little bit tricky here, is that we plug in the CGO solution, we actually get attenuated geodesic transform on R2. So F here is the difference of the coefficient over the linear parameter epsilon square. And we take the Fourier transform only in terms of the first variable, the x1 direction. And then from there, you actually get the attenuated geodesic transform on R2. And still, it's kind of a analog of the Fourier transform. So this is where this kind of analysis digress into different kind of integral transforms. So you sometimes run into this integral geometry inverse problems, like what Gunther was talking about, that kind of a geometric inverse problems. So this can be generalized to the inverse problem on admissible transversely anisotropic manifolds. These are essentially those manifolds with the metric allows you to have this kind of cylindrical coordinate so that you can construct a similar kind of CGO solutions for Maxwell's equations. I guess this is a little more
but Ting, I have a question. So then don't you, if in the case of this admissible case, admissible transversely anisotropic manifolds, right? So then don't we need to assume that the attenuated geodesic ray transform can be inverted?
Yes.
Is that an assumption?
Right.
Because for small attenuations, I think it's okay, right? Because I think you can use the variation of the Pestov identity or something like that. Right. But what's the nature of the attenuation here? Is it small, or there is no you cannot put any smallness assumption?
Right. So I think I don't recall exactly, but indeed we have to assume that you can solve this. You can invert this geodesic ray transform too, by assuming that it being simple or.
Okay, and in the case of R2, then you use this Novikov's result or this Buchheim's result. Is that right?
Say that again. Sorry, I didn't catch.
In the case of R2, the attenuated in the R2, you use this Buchheim's or this Novikov's result for this, the inversion of the attenuated ray transform.
Right. You mean? Sorry, I didn't catch exactly your question.
Yeah, the question is about the inversion of the attenuated ray transform in R2.
Right.
I'm just wondering, the thing is, I think this was done by Novikov, right? Is that right?
Right. Yeah, I think there's some results by him, Novikov.
I see. Yeah. Okay.
We just directly applied their results there. Yeah.
Okay.
Right. I guess I should say with the linear phase, I guess we can still stretch here, but with kind of different amplitude choice. The thing is, with the Ola-Somersello, so I want to come back to this question. With the Omersello choice of the CGO solutions, I should say here in this CGOs, the amplitude looks like this, essentially of zeta, which is the same as the phase here. If your amplitude looks like this, here sort of explain why you cannot get uniqueness by looking at the inverse problem for linear equations, say Calderon problem. I think this is an interesting comparison between the two. That's also why you want to look at the reduction to Schrodinger equation. So let me try to explain what I wrote down here. Is that on the right is what we usually do for the Calderon problem proof, where you reduce everything into Schrodinger equation case. And the boundary identical DM map will give you this integral identity, really in terms of the solution for the Schrodinger equation. And then you have the V1, V2 being the CGO solutions plug in, and the product to give you the Fourier transform of the Q1 minus Q2. But on the left-hand side, if you think about it, you can still do the same thing for the conductivity equation itself by deriving an integral identity looking like this. And if you also use Uj being the CGO solution coming directly from the Schrodinger equation, meaning that you have a CGO solution V, and you simply multiplying that by the conductivity, square root of conductivity, you get the Uj, 1 over that. So the thing is, when you take the gradient, since the product is at the gradient, and then you have the, yes, free variable here, but you also have the first leading term should be Z1 dot Z2. Okay, so you want to keep Z1 dot Z2 being the leading term, so you don't need to worry about the remainder term being becoming the leading term. If the Z1 dot Z2 is no longer of the magnitude square term, then the other two terms become leading term, part of the leading term. And since we don't know R1 and R2, so this definitely doesn't help us to determine gamma 1 minus gamma 2. So, and you will find yourself hard to find the complex vector zeta 1 and zeta 2 such that the dot product is still keeping to be the magnitude of zeta squared, or in another word, tau squared. So tau being the size of the zeta. So the same thing happens with Maxwell's equation. If you look at the inverse problem for linear Maxwell's equations earlier, remember what we did for the proof, at least using Ola Sommersello's reduction. This is the integral identity we derived, where Y1 is the CGO solution for the Schrodinger equation. X2 is the solution for the first order Dirac system. However, you really can say that it is a solution for another Schrodinger equation. And then this is very similar to this equation here for the Calderon problem. You have X2 and Y1 being CGO solution for a certain Schrodinger equation. But if you use the integral identity directly derived from Maxwell's equation, and the E1 and the E2 here are very similar to the gradient of U1 and the gradient of U2 in terms of CGO solutions. So what that means is that the amplitude in the CGO solution for Maxwell's equation will be of zeta. So really E1 dot E2 essentially is zeta 1 dot Z2. So that also you lost the leading term property, and the remaining term will dominate. Then again, you cannot track them, so you cannot get epsilon 2 minus epsilon 1. So what I'm trying to say is the integral identity for the higher order linearization for this type of inverse problem we are using essentially only looking at electric field and magnetic field. So it's more of the left column situation. So when you plug in CGO solution, you have to be very careful. And sometimes you run into this problem, like when you have a product of say 4 solutions and you lost the leading term. They become 0 or no longer of the leading orders. So that was the situation why we tried the linear phase the CGO solution. And that's why also why we want to go through this different limiting column weights CGO solutions. Okay, I hope I explained that whole thought clearly, but eventually we plug in these CGO solutions and we solve this problem. Okay, back to track. This is to show the same thing for the second harmonic generation case. Recall that we have this integral identity of product of three solutions, they are all linear solutions. So here, in this case, you also have a similar problem as before, but we use the scheduler solutions with different type of amplitude. So the amplitude before using Euler-Somerset reduction, they are essentially of zeta. Zeta is a linear phase in the exponential. But in Euler-Somerset, their amplitude here actually satisfies zeta dot A being 0. Okay, so you don't need to really understand these choices of the complex phases and the amplitudes, but really what I'm trying to show is we can choose the zeta 3 complex vectors and corresponding amplitude such that also A tilde to omega. And when we plug in to this integral identity, the second term vanishes, at least the leading term vanishes. And then you get a Fourier transform of chi2 minus chi1 dot asymptotic amplitude of E tilde omega. Okay. As I mentioned, the CGO solution we're choosing here is such that the amplitude dot zeta being 0. And we can actually, we have 2 degrees of freedom to choose this amplitude such that first this is true, and then we get the Fourier transform of the difference. Keep in mind they are vector valued functions in Cauchy, and the dot perpendicular direction to Cauchy being 0. So this really gives you the curve of the difference of these vectors being 0. And you can also choose another amplitude, A tilde omega, such that a dot Cauchy being 0. So that gives you the divergence being 0. So these two together tells you that chi2 minus chi1 has to be 0. So you would think a similar result before could say, okay, if you have a vector valued potential nonlinear potential in your equation, sometimes you will get uniqueness up to some diffeomorphism or some uniqueness of the conformal class, but it's not the case here. You can show that indeed you get full identical for the parameters. Okay. That concludes the proof for the inverse problem for nonlinear equations. I know you probably have questions on here and there on the modeling and also the geodesic Fourier transform part, I guess. But yeah, we can discuss that more afterwards if you are interested. I guess I still have 10 minutes. Maybe I spend a little time to talk about this magnetic Schrodinger equation case. The reason why I want to talk about this is also it will become the it's a nonlinear equation again. We use this higher order linearization approach. Eventually, we'll have an integral identity of difference of the parameters against the product of several solutions. But things are a little bit different when you have a magnetic potential involved in this scalar equation. Okay, so we consider this so-called magnetic Schrodinger equation. Q here will be the electric potential, Schrodinger potential. We assume it being nonlinear, saying it depends on the U nonlinearly. And also you have a magnetic potential A being a vector potential, also nonlinear in U. So these are the assumptions on A and Q. They are holomorphic in terms of the second variable. So you can have a Taylor expansion in Z or in U. And what we're trying to recover are the Taylor coefficients in this expansion for the different order terms, so that we get a full information of this nonlinear coefficient. Here we assume AX0 being 0. and QX0 and first order QX0 being 0. This is just to guarantee 0 is a solution for this equation. Okay, and then you can do linearization. Yeah, also the linearized equation for this equation is only the Laplacian. So that's apparently is a restriction of this kind of approach when you're talking about using partial boundary data as a measurement. I'll show you a little bit more why that's the case. Okay. So the partial boundary DM map defined here for this nonlinear magnetic Schrodinger equation is again mapping the derivative data to the Norman data, where you here, the derivative data here is supported on part of the boundary gamma 1. And this Norman data, Norman boundary condition is supported on gamma 2. And gamma 1 and gamma 2 are arbitrary open subsets of the boundary. Okay, so these are very relaxed partial data. So the inverse problem to recover, as I said, the Taylor coefficients in the expansion of these nonlinear coefficients parameters. Okay. So again, we use the higher order linearization approach for the DM map and to do the two polarization directions. And as a result, by looking at the second order term in the expansion, showing that we can derive this integral identity. Okay, this is very similar to the one we had before. Without the magnetic potentials A, so Q tilde, when I add the tilde, it really is the difference of the two parameters. It's just for simplicity of the notation. Okay, so if we look at the second order terms, for example, then we have Q tilde being the difference of the second order Taylor coefficients. And if we don't have A, then we just have the difference of the two potentials test against integral against the product of three linear solutions. So V1, V2, V3 here are all solutions for Laplacian equations, which is a linearized equation for the original magnetic Schrodinger equation. That's why we have this condition to guarantee that the linearized equation of this nonlinear equation is just a Laplace equation. Okay. But with the magnetic potentials, you have these two extra terms. So that's something people haven't done, and part of the novelty of this work with this is the joint work with Professor Rui Lai from University of Minnesota. Okay, so we look at this integral identity. You have a combinations of difference of magnetic potentials and the difference of electric potentials. Okay, and the solutions, as I mentioned, V1, V2, V3 are solutions for linearized equation. In this case, it's just Laplacian. But since we are talking about partial data here, for this to be true, you need the support of V1 and V2 on the boundary to be in gamma 1 and support of V3 to be in gamma 2. Okay, and this is partly due to that you only have the identical DM map for the partial data. So now the question becomes, where can we find the proper solutions, harmonic functions in this case, such that these properties, these assumptions are satisfied to give us information of A tilde and Q tilde. Okay. Here is just to summarize some previous results using the same idea. This first one is just to look at the case without the magnetic potential. So only here A, the little a will be Q. Okay. So this assumption is also to guarantee the linearized equation is Laplacian and 0 is a solution. Okay. And in another paper by Krupchik and Urman is to look at the other type of nonlinearities in the Schrodinger equation. This is like for m being bigger than 2, so quadratic or higher order. So this is simple. If you have m order nonlinearity, you have q1 minus q2 times m plus 1 harmonic functions. And if you have nonlinearity to be the product of two gradients, then you will have a product of the two gradient of harmonic functions multiplied by the third function. So you can see the trend here. All these integral identities are all for partial data. So M solutions will be supported on gamma 1, and the next one will be only supported on gamma 2. The same here. So all these inverse problems now are reduced to finding solutions for harmonic functions, which vanishing here and there on the boundary, so that this integral identity gives you the information of the coefficients. And this dates back to as early as this work, where you look at well, this is the case, I guess, for the linear equation. But here you have, so for the partial data Calderon problem, where you have this integral identity as a comparison. But in this case, U1 and U2, these are residual solutions for the linear equations. These are no longer just harmonic functions. So the construction of these solutions are different from the construction of harmonic functions vanishing on the boundary. I'll be focusing on the construction of harmonic functions vanishing on the boundary. And the earliest result of discussing these kind of functions, harmonic functions vanishing on the boundary, is done in this work, the second item here, where they consider the Calderon problem but linearized at the potential Q being 0. So this is the same integral identity but from different context, kind of linearized inverse problem, where V1, V2 now being harmonic functions and supported on gamma 1 and gamma 2. Okay. I guess I have 2 to 3 minutes to just show you the steps here. What they did, yeah, this is the paper I'm talking about in this work. So they constructed such solutions or harmonic functions being kind of similar to the residual solution, leading term of the residual solution, also plus a remainder W here. But this remainder is not a residual remainder. This is completely coming from the Laplace equation, and trying to cancel the exponential here on the boundary so that the whole solution is supported on gamma on the boundary. I should say U here should be V. Okay. So the W, keep in mind, is only account for this cancellation on the boundary. Okay. If you plug in these solutions, V1, V2, looking like this with the W, and the first terms gives you a kind of free transform of Q1 minus Q2. And then the W terms all goes to the right-hand side. And you can derive this kind of decay as H goes to 0. 1 over H is like a tau before. 1 over H goes to infinity, so H goes to 0. So you have this decaying property, okay, exponential decay. But this is only true when the zeta 1 plus zeta 2 being close to the E1 direction, okay? There's some technique inside of this coordinate system, but really what I'm saying is the choice of Z1 and Z2 is directly linked to this decaying property, and it's not all free, meaning that we cannot show Z1 plus Z2 being rich enough so that you get free transform of Q1 minus Q2. And how do you extend this kind of exponential decay to other directions, other free directions? That would be, they introduced this sort of harmonic extension technique carried over from Kashiwara's watermelon theorem, a variation of the proof of that theorem, to really extend this exponential decaying to other directions or other Fourier directions, so that you really get the Q1 minus Q2 Fourier transform, and in order to get the uniqueness. Okay. These are two as I mentioned, the two works I mentioned earlier with different kind of nonlinearity, they use the same technique to prove the density of the product of solutions, okay, by essentially deriving estimates looking like this. Okay. For us, we modified the argument a little bit because we have the two extra terms for the magnetic potentials. So first, what we did is to use the product of two solutions being dense that was established earlier in this work already. And that basically tells you that you can immediately get what's in the bracket being 0. Okay, and from there, we choose V3 being this special solution again, exponential plus the W3 to cancel the exponential on the boundary. Sorry, the asymptotic in H will give us A tilde. Keep in mind that's the difference of the first order of magnetic potentials. And we can show the dot product with zeta, with a complex vector in the exponential of V3 being 0. And this is only for several zeta locally near a boundary point of gamma 2. Okay, so using this, we can only show A tilde is the difference of the magnetic potential being 0 in a neighborhood of gamma 2. Gamma 2, keep in mind, that's where the Norman data is supported. Okay, and then we derive this bootstrap local to global step, and that helps us to derive that A tilde being 0 in the whole omega using the unique continuation technique. And once you have shown A tilde being 0, and you can immediately get Q tilde being 0 using similar argument. So that's the analysis what we did, slightly different and was not done before. Okay, so that is the proof. I guess the idea here is to show you that you can choose different type of solutions. Of course, there's a restriction of your linearized equation here being just Laplace equation, and you are looking at the pool of harmonic functions, which probably is much larger than other type of solutions. But it's an interesting macrolocal analysis, and, or especially this very high, very advanced technique using the harmonic extension. Okay, I stop here. Sorry for overtime.
Thank you, Ting. Any questions? So any questions from the audience? So I have a couple of questions, with regard to the last part. So I suppose there is no gauge invariance when you also assume that the A also depends, there is a nonlinear, the magnetic term is actually nonlinear. Is that right?
Right. Okay. Yeah. We assume A being
quite surprising.
Right. I should say, I mean,
yeah, so
it's not really completely surprising because here they also have a sort of first order nonlinearity here. And the proof actually, what I should say.
See, but
yeah, so it's all here because so when you have these solutions, and it's all about whether you can have this beautiful exponential here. Sometimes if you have different nonlinear terms, and in front you will have some like dot product with different directions, and you cannot extract all information of Q1 minus Q2. I don't know if I explained clearly. For example, in our case, if you directly try to do the same argument as before, then here you will have zeta dot A tilde, for example. V3 will be something like this. And when you take the gradient of this, you will have zeta. And then you will have A tilde of zeta. And then that will cause some issue. So I think you can also looking at even Maxwell's equation, and you probably also run into similar questions. But yeah, I guess.
And the other, yeah, I see. And the other question is, can you remove that holomorphicity assumption? The one that just as you introduced this slide, the holomorphicity in the z variable.
I guess you can.
Actually, maybe the previous slide. Yes, here. Yeah.
Right. Sorry, I should. Yeah, here. Right. I guess you can. I shouldn't say it's holomorphic, meaning so much smoothness in terms of z. I mean, you can have it to be any order of differentiability. Then you can use I mean, the analysis just involve estimating the remainder term. Meaning you can use what kind of Taylor tail you are using. You can use the integral term for the Taylor remainder and just control that term is fine. So I don't think this is completely important.
I see. Okay, so for some reason I was thinking that this part is crucially used in the Runge approximation step, but maybe I'm not thinking it correctly. The holomorphicity
approximation, I think they are only considering linear equations. So
I see.
They don't care about the nonlinearity here. So it's all harmonic functions. So that part
is.
I
see. Right. Okay, I see. Okay. Yeah. Any other questions?
Yeah. So I have one question. So the thing is that for this kind of for this nonlinear thing, nonlinear magnetic Schrodinger. So means these arguments will lead to some stable determination results, or
these you mean is there a kind of a application?
Yes. Are there results on stable determinations, or?
Right. I guess there's no special example I'm looking at, just because if you look at linear magnetic Schrodinger equation, there are particular one direction Calderon problems for magnetic Schrodinger equation, the linear ones. So I mean that has a physical model, of course, because A here is just corresponding to magnetic potential, right? And I think it's reasonable assuming that also being nonlinear. So, but I don't know if you can generalize this to depending on the gradient of U as well. I mean, the analysis probably will be more involving. Yeah. But I think if you are looking for, then you can find some physical literature to have some nonlinear magnetic potential.
So means one help is that this kind of nonlinearity makes it easy to consider this partial direct element. But means in the direction of stability estimate, is it helpful to get better stability or something? Means this kind of means nonlinearity, does it improve the stability estimate, or
does it include what estimate?
The stability estimate, like this log stability will be improved something better or something, if you consider nonlinear problems, or means
yeah. So what Saumen is asking is can you get better stability estimates? See, the thing is in the usual Calderon, right? You only get like log or log stability, things like that. But if you have nonlinear equations, does the stability actually improve to something better than
doubt about that, but why do you think that could be some, you have some intuition that makes you think
No,
that?
no, just asking because no.
Yeah, I mean, probably not, because you can see these analyses are all based on this kind of integral identity. So, and from the experience of the stability for the linear equations, Calderon problem, where you have CGO solution, but really it becomes this kind of is the optimal exponential solutions you are plugging in. And even for this, you plug in 3 solutions of exponential type, then I don't see that you can get any better stability, at least using this approach.
Okay.
So,
So
in
in
some
the
sense, I think
hyperbolic.
logarithm is optical, optimal.
Okay. Yeah. So, yes, I think the in the hyperbolic case means hyperbolic nonlinearity. So there is some better stability estimate.
Right. Hyperbolic in general is better because you have essentially multiple frequency information, and you can think in that way. And especially there are stability discussions of frequency dependence for the Calderon problem, of course. They can show kind of better stability when you have higher frequency omega. So yeah, and if you have the full spectrum frequency information, maybe you should expect better stability. But I think that's the different. That doesn't depend on whether it's linear equations or nonlinear equations. So,
Okay. Okay. Thank you.
thank you.
So any other questions? So if not, Ting Zhou, thank you very much for this wonderful 2 lectures, for taking the time, and it was really wonderful. Thank you very much.
Of course, yeah. Thank you for the opportunity. I'm welcoming any questions anytime. Just
thank you very much, and I hope to see you sometime, in conferences or something like that very soon.
Sure.
Thank you.
Okay, see you.